Okay, so question number 4. To just draw Lewis structures for the following molecules. So first we have sulfur hexafluoride. Let's calculate the total valence electrons in this molecule. So sulfur has 6 and fluorine has 7, but there are 6 fluorine atoms in total. So if we added it all up, we get a total of 48 valence electrons. So now let's just draw sulfur as our central atom, and then the 6 fluorines arranged as symmetrically as I can. And now I'm just going to show all of the lone pairs on the terminal fluorine atoms. So if we recall that each bond contains 2 electrons, and we have a total of 6 bonds, that is 12 so far. And then each fluorine atom has 6 electrons in the form of lone pairs. So 6 times 6 is 36, plus 12 is 48. So this is the following Lewis structure for sulfur hexafluoride. Okay, so now let's do the next molecule, aluminum chloride. The total valence electrons are the following, where aluminum has 3 and chlorine has 7, but there are 3 chlorine atoms, so we have a total of 24. Okay, so now let's draw aluminum as our central atom and the 3 chlorine atoms around it, showing all of their lone pairs. If we were to count out how many electrons I've drawn so far, 2 in each bond, this is already 24, so we don't need to add any additional lone pairs on aluminum. And that is the following Lewis structure. Okay, so let's try to fit carbon disulfide, the bottom here. For the total valence electrons, carbon has 4, sulfur has 6 times 2, which is 12. So we have a total of 16 valence electrons in carbon disulfide. So now let's draw carbon as our central atom, single bonded to the 2 sulfurs. So I've only drawn 4 electrons so far because I have 2 bonds, but I'll draw them as double bonds just so that carbon can have a full octet, and we can draw the remaining on the sulfur, and then this should give us 16 valence electrons. Everything has a valence, a full octet, so that is correct. Then I'll try to fit the remaining Lewis structures on the next page. For D, we have selenium bonded with 4 fluorines. So selenium has 6 valence electrons, and each fluorine atom has 7, and there are 4 of them in total. So 28 plus 6 is 34. So let's draw selenium as our central atom, and the 4 fluorines all around. showing all of their lone pairs. And if we counted it out so far, we have 4 bonds to the fluorine. So 8 times 4. So we have 32 drawn so far. So for the last 2 electrons, I'll add them as lone pairs on selenium. Okay, so now let's move on to E. We have beryllium bonded with 2 chlorine atoms. And note this molecule does not follow the octet rule. So this is helpful for us. So beryllium has 2 valence electrons. Each chlorine atom has 7 times 2. So we need 16. Let's draw beryllium as our central atom and the 2 chlorines on either side. And we'll just show all the lone pairs on chlorine. And if we added up all the electrons so far, we now have 16. So beryllium, again, is an exception to the octet rule, so this would be our correct structure, Lewis structure for beryllium dichloride. And now let's do the last molecule. So dinitrogen Tetra oxide. So nitrogen has 5 valence electrons times 2, 10. Oxygen has 6 times 4 is 24. So in total, we have 34 valence electrons in this molecule. So now let's draw the 2 nitrogens together. And then we'll symmetrically try to draw all the oxygens, single bonded. So now notice that the 2 nitrogens in the middle don't yet have a full octet. So I'll draw each one as a double bond. And let's see how many electrons we've drawn if I just fill in the remaining electrons. So far we have 7 bonds, and we have, let me count out all the electrons we have drawn so far. So we have 34 already, and if we were to show all of the charges, the 2 nitrogens would have the positive charge, which is good since nitrogen is the less electronegative than the oxygen, which should hold the 2 negative charges. So now that all the charges cancel each other out, we have a neutral molecule. So this is the following Lewis structure for dinitrogen tetra oxide. Okay, so let's see what the junior tutor said, starting with our first molecule. When drawing Lewis structures, the total number of electrons that need to be distributed is counted first by adding the valence electrons of each individual atom. If a formal charge is present on the molecule, this is also taken into account in the total number of electrons. The skeletal structure is first written by distributing bonding electron pairs. Then the lone pairs are distributed until the octet is completed. Formal charges are added to the atom if the number of electrons does not satisfy the octet to indicate that an electron has been transferred, added, or removed. Structure with the least number of formal charges or has the smaller charge is the most stable. For sulfur hexafluoride, they have the same Lewis structure, is correct. For aluminum chloride, there are 24 valence electrons and got the same Lewis structure as well. Carbon disulfide, you see that the carbon has the 2 double bonds. This is correct. Selenium tetrafluoride has 34. So this is correct as well. Beryllium chloride has 16 and doesn't follow the octet rule, so this is correct. Dinitrogen tetroxide has 14, and the bond pairs and 4 pairs are in 2 double bonds, yep. And then they show how the charges would cancel each other out. So this is correct as well. So this solution is correct.